So last time we started the zigzag product. So for that, let us recall the replacement product, right, which is used to reduce the degree that has grown because of the earlier products. So what you do to reduce the degree is you take this replacement product with a graph G prime, where in G prime the number of vertices is equal to the degree of G, and the degree of G prime is much smaller. Okay, so we used big D and small d. And then what you do is whenever you have to walk or pick a neighbor in the graph G, you make that decision by walking in G prime. That was the main intuition, and then there was this extended definition and all. So that gave us the replacement product. Basically, its size grows to n times big D, and the degree becomes originally it was big D, now it becomes d small d plus 1. So degree falls drastically. So based on that, now remember that we couldn't do or we didn't do the spectral analysis for the replacement product. We'll do it for a different product, which is called the zigzag product. So in the zigzag product, you basically look at length 3 paths. It's kind of cubing the replacement product. But you did this in a zigzag way. So you zig in the cloud, then zag out of the cloud, and again zig in the cloud. Okay, so it's kind of zig, zag, zig, 3 steps. That gave you the zigzag product, which is denoted as G circle Z G prime. So here the number of vertices is the same as n times big D, and degree grows slightly to small d square, but small d will be much smaller than big D. So this is still much smaller than big D. And we had these formulas. So now the normalized adjacency matrix of zigzag product, this A Z A prime, A product A prime is B A hat B, where B or A hat is actually the step you take outside the cloud. So that is dependent on A, and B is the step you take inside the cloud. So that is dependent on A prime. Okay, it is just so A hat and B are just blown up versions of A and A prime, and then you multiply the 3, so you get B A hat B. That's the new adjacency matrix normalized. Okay, so A Z A prime is both stochastic and symmetric, that we had observed last time. Now we will do the spectral analysis. So the major theorem is due to Reingold, Vadhan, Wigderson. So this theorem says that if the second largest eigenvalue of G is at most A, or let us say equal to A, and that of G prime is B, then the lambda of zigzag product is A plus 2B plus B square at most. So to understand this, the meaning of this, think of A and B as small, and Also remember that they are both fractions below 1. So b square is quite small. So this is like a plus 2b. Okay, so this is think of this as something additive. So if you started with small a and small b, then this spectral norm is small, it remains small, and the advantage of the zigzag product is that degree also has fallen. Okay, so the earlier products, they were increasing the size of the graph. This product decreases the degree. Moreover, it keeps the spectral gap intact. So that's the import of this theorem. Let us prove it. So let us say the product, call the product A Z A prime, call it M, that's the zigzag product, and we will now study the spectral norm of this matrix. So recall that M is equal to B A hat B, where A hat is A hat is a permutation matrix dependent on G or A, and B is dependent on A prime. So B is tensor product. It is just a blown up version of A prime. It helps you move in the cloud, one step in the cloud, and then go out by A hat, and then again move in the cloud by B. Okay. So let us do the following. So we will write M in a different way, and that we will start by rewriting B matrix. So you first break up A prime by this all one matrix J. Okay, so J by D we take out, and what remains is A prime minus J by D, where J is all one matrix. And this A prime minus J by D we will call E. So why did we do this? So we are doing this so that we separate we separate B into two kinds of matrices. The first matrix is expected to have a larger spectral norm, and the second one smaller. Okay, that is what we want. We want to break it up into large norm, small norm, and then we will bound the small norm separately. So define J bar to be the first part, and E bar to be the second part. So we have broken B into J bar and E bar. As I said, idea is that J bar is kind of the main term and E bar is the error term in terms of spectral norms. And then we will try to bound the error. So what this means is M is equal B A hat B is J bar plus E bar times A hat times J bar plus E bar plus J bar A hat E bar plus E bar A hat J bar plus E bar A hat E bar. Okay, so there are these 4 terms when you multiply out with J bar J bar, J bar E bar, E bar J bar and E bar E bar. Remember that this multiplication is possibly non-commutative. So these are 4 terms, could be different. The last 3 we will consider as the error, first as the main term. So each of these 4 will upper bound the matrix norm first. Matrix norm or the spectral norm, which is lambda A for a matrix is, we will denote it by this, which is further defined as the max over AX divided by X for X orthogonal to 1. Or in other words, action of A on unit vectors orthogonal to 1, what is the maximum shrinkage? That is what this norm measures. Okay, and we will also use another norm. So this is to do with the second largest eigenvalue, right? And there is another norm. Let LA be the max over all X. So the shrinkage of unit vectors by A over all the vectors. Okay, this is the norm. This is another norm. This will be bigger than the previous one. This is related to largest eigenvalue. And the previous one was the second largest eigenvalue of A. Okay, so these are the 2 norms of interest. We are interested in the gap between the 2. So observe that for this error matrix E bar, matrix norm also or spectral norm is at most the L norm by definition, and E bar was A prime minus J by D. We want to upper bound this. So let lambda 1 to lambda D be the eigenvalues of A prime. Such that they are ordered A prime comes from G prime, and that was graph with number of vertices big D, right? So it has big D many eigenvalues starting from 1, and we are interested in how small lambda 2 is, the magnitude. Since these are eigenvalues, you can write A prime in terms of them and eigenvectors. So write A prime as lambda I vi transpose I1 to D or orthonormal eigenvectors. Of A prime. So this I leave as an exercise. This is a standard fact from linear algebra that that A prime has well, it has real eigenvalues, then it has real eigenvectors, and in terms of in fact, it has eigenvectors which are unit and orthogonal, which means that they form an orthonormal basis. With respect to that, you can actually write A prime like this, sigma lambda I vi transpose. And let us use this expression to bound norm of E bar. So A prime minus j by D. Now notice that V1 is just all coordinates 1 over square root D, right. So vi transpose is actually j by D and lambda 1 is 1. So this is equal to the L norm of what remains, which is lambda I vi transpose for I2 to D. And this one, how do you upper bound this? So notice that sigma lambda I vi transpose, when you act it on a unit vector x, right. So what does it become? So it becomes lambda I times vi times this number, real number vi comma x bar, and you are interested in the norm of this. And remember that vi's are orthogonal. So this is in fact equal to norm square. So what we will use here is that x bar you can write as a combination of this orthonormal basis. So say x bar is alpha I vi, and when you do this, then the above thing is the same as vi x bar. So vi x bar will only extract alpha I. So you'll actually get this. That is the point. Okay, so you actually, when you take inner product of x bar with Vi, all the Summon's inner product vanish except that of Vi, which gives you alpha I. And also remember that Vi is a unit vector. So you are left with actually sigma lambda I square alpha I square. And sigma alpha I square is actually 1. Okay, so this expression is at most the highest lambda I, which is lambda 2. So that is what we get. We get that this sigma lambda I Vi transpose. So the action of A prime on x bar, this norm is at most value of lambda 2. So we go back, we know that that is at most the value of lambda 2, which is the matrix norm of A prime, which is equal to B. So we have upper bounded the matrix norm of E bar in this way. Okay, so let us now see where we are. So we broke up M by breaking up B and then multiplying. So we had these 4 terms, J bar, A hat, J bar, then we have J bar, E bar, E bar, J bar, E bar, E bar, and we have an upper bound on the matrix norm of E bar. So let us apply this on the sum. So going back, we have by triangle inequality that the matrix norm of M, which is defined by the norm of a vector, right, the action of M on X. So on a vector norm you can apply triangle inequality, so hence you can apply it on this matrix norm also. So you will get that this is less than equal to the norm of first term, which is J bar A hat J bar plus J bar A hat E bar plus E bar A hat J bar plus E bar A hat E bar. And then you use the multiplicative property of norm, okay, which is norm of product is less than equal to product of norms. So you will get, first one I don't change, I keep it the same, but second one I change to that. Plus similar things. So first main term and then the error term I have written as product, sum of products. And I just point out that this we can do since A bar or A hat, J bar, E bar, they map one bar orthogonal to itself. Okay, they preserve this orthogonal space orthogonal to 1. So hence by the definition of matrix norm you can easily see that this multiplicative property is there. And now I can write this as, I can upper bound. The main term I don't analyze now, I am postponing that, but these error terms I'll use the trivial bound. So for J bar matrix norm, it cannot exceed 1. Same for A hat norm. E bar I have shown to be B at most. Okay, let's use this approximation or upper bound. Right, so I get this plus I get 2b plus b square. Okay, that is where we are. So we have a main term and then we have this 2b plus b square, where b we got from this norm of E bar from the previous calculation. Okay, let us now estimate the main term. So now consider J bar A hat J bar norm. Let us first consider this matrix. What we will show is that this matrix is it of course comes from A, but the exact relationship is tensor product. Okay, so remember J bar is tensor product identity with J by D, right, and A hat is the permutation coming from A, coming from graph G. So it's not very surprising that when you multiply A hat with J bar on left and right, then you again get a tensor product. Let us just check that. So let us check the UIth VJth entry of this matrix. So you have to recall how the rows and the columns of A hat were indexed, right? They were indexed by using this rotation map of the graph G. So let us look at row UIth and general column VJth. So this entry is following matrix multiplication. It's the J bar UIth row times A hat matrix times J bars VJth column, right? But this row and column is simply this what was it? J bar was identity times J by D. Yeah, so these entries are just 1 by D. I mean, in the kind of the block diagonal, in the block matrix representation, it is 1 by D. In the block diagonal locations, other locations, it's 0. So what you will get when you multiply these two things to A hat is, you have to check this, you will get actually the UVth entry of A hat. Yeah, so there is a 1 by D factor which gives you 1 by D square, but then there will be a multiple of D also, so you will actually get 1 by D. So you will get this. You will get the UVth entry of the matrix A divided by D. Okay, just check this. It follows from the definition. You just have to go back and compare the definitions. And AUV by D is actually the RHS matrix entry. So So, if you look at the uith vjth entry of this tensor product A with j by d, then you will see that it is just AUV divided by d, this factor 1 by d. So, remember that in this tensor product what is happening is the UV is actually indexing A and the IJ is indexing J. Okay, so this IJ goes away. You just get A U comma V. So, you can check this, and that shows that J bar A hat J bar is actually quite simple to begin with. It is just A tensor all one matrix and normalized by D. So, we want to understand the spectral gap of this matrix A tensor J by D, and it will boil down to the spectral norm or matrix norm of A. So, that is how you will get small a. Okay, let us just finish that part. Note that the eigenvalues of J are the largest one is of course 1, everything else is 0. Okay, this is a small exercise that you can do. And of course, this 0 is repeated. So, overall the number of eigenvalues has to be the dimension of this J, right. So, you know the eigenvalues of J and you know the eigenvalues of A. So, you know the eigenvalues of tensor product. So, J times all one vector is all one vector, and for every vector orthogonal to 1, Jx is 0. Okay, so 1 is an eigenvalue, and then the whole space orthogonal to 1 is an eigenspace. So, which means that you understand the overall eigenspace of J, and the eigenvalues are then just this 1 and then all the zeros repeated. So, this means that the norm of A tensor J by D this will be, this is at most the, I mean whatever the eigenvalue second largest eigenvalue was of A, that will remain unchanged because it is only being multiplied by 1 or 0, right. So, hence overall the second largest eigenvalue will remain that of A. Which is equal to A. And so, we know now that J bar A hat J bar's norm is A. So, this means that going back, the matrix norm or spectral norm of M. So, this finishes the proof of the theorem by Reingold, Vadhan and Wigderson, and it gives you a very good understanding of the spectral gap in the case of zigzag product. So, let us write that down in terms of algebraic expansion. So, G prime are n big D lambda 1 and big D small d lambda 2 expanders. Then for the zigzag product, as the previous theorem showed, the algebraic expansion will be there. Okay, and the other parameters, so the number of vertices is multiplicative n times d. The degree is little d small d square, and the spectral norm is lambda 1, which was before, but now it may increase slightly. So, that is 2 lambda 2 plus lambda 2 square expander. Okay, so this lambda 2 we have to pick small enough, so that lambda 2 plus lambda 2 square is not that much. Thus, this zigzag product reduces the degree dramatically. Of course, assuming that small d is much smaller than big D, without worsening the expansion. So, without increasing the lambda too much. So, that is the point of zigzag product. Okay. So, this last product together with the earlier products gives us all the tools to construct expanders that are explicit and the expansion or spectral norm is constant. So, let us finish that. So, using these products, we give a strongly explicit construction or family of expanders. Now, what is this strongly explicit business? The ith neighbor of U is polynomial in log V time computable. Okay, so the bits needed to describe U is log of n or log of size of V, and the bits needed to describe I is there are only d neighbors, so that is log d, which is constant. And in terms of this input size U comma I, this is polynomial time algorithm. Okay, so that is strongly explicit. So, in terms of this time, actually the graph size of V can be exponential. So, it is a very large expander, it is a growing family, degree is constant, expansion spectral norm is constant, and it is very, very explicit, polytime explicit. So, there exists strongly explicit d square lambda expander family for infinitely many constants d and lambda. So, d being numbers, natural numbers, and lambda being a positive fraction less than 1. Now, further away it is from 1, the better expansion. Okay, so now we just have to give you the sequence of products to do. In the base case, you just start with some constant sized expander, and I mean, even if you just pick a random connected graph, it will be of that type. It will be a constant sized constant spectral norm, and starting with that, you to make it bigger, you do tensor product, and to improve expansion, you do path product, and by that point the degree would have grown. So, to reduce the degree, you do zigzag product. That is the sequence. So, we will recursively construct expanders GK such that GK has 2 raised to order k vertices. Okay, so remember that graph will be expander will be very large. So, it will have these 2 raised to k many vertices, but everything the complexity, the time complexity will be polynomial in k. So, it is basically a recursive construction. The k steps, you will get this GK in k steps kind of. So, what are these steps exactly? So, let H be a d raised to 8 sized d degree 0.04 spectral norm expander. So, this you find by H could be found either randomly or by known constructions. So, this is not the hard part, this is all easy to do. You can find H because it is constant sized, constant expander. Then you start the process, okay, the k steps that will give you GK. So, let G1 be H square, that is H cross H path product. This you know is vertices will not change. So, d raised to 8 many, degree will square, but the expansion will also improve drastically. So, that will also be squaring. Right. So, this is G1 is a very good expander, but the problem is that it has constant size. We have to grow that. Also, for technical reasons, we will keep G1, G2 equal and then G3, G4 equal and so on. So, let G2 remain G1. For odd k, the definition is GK plus 1 is the same as GK. Will do the construction recursively. So, you actually go down to k minus 1 by 2 and take tensor product with itself. Okay. So when you go to gk minus 1 by 2, obviously by recursion or by induction, that was already constructed, so you have access to it. Although it's a very big graph, but you have access to the algorithm that produces it. So that algorithm, you can actually do tensor product and get a different algorithm to get this tensor product graph or expander. Do that, then you do the path product, square it. Now the degree has blown up, so reduce that by zigzag with h, right. So h has degree d, so this thing in the end will have degree little d square. That's how you do it. So the claim is that for all odd k, gk is d raised to 8k d square 0.1 expander. Okay, so d, remember, is a constant. So d raised to 8k is like 2 raised to k, 2 raised to order k. It's exponential in k sized graph. Degree is d square, so it's constant, and expansion is 0.1 spectral norm. Okay, so this is, and this is true for every odd k. Every other one is equal to the prior one, but overall as k grows, this is giving you a bigger and bigger expander. Still constant degree, degree the same, expansion the same, upper bound. Okay. So in the base case, we have shown this. It's true for k equal to 1. By definition, that was h square, so we have shown d raised to 8 d square 0.04 square, so it's even better than 0.1. Let's now do induction. So what is the number of vertices in gk? So you have to recall the 3 products: tensor product, path product, zigzag product, and how the size of the vertex set grows. So d raised to 8 k minus 1 by 2 is the by induction hypothesis on gk minus 1 by 2. Tensor product will square it. Path product will not change it, and zigzag product will multiply it with d raised to 8. Vertex set of each, which is also d raised to 8. Yeah. So that's d raised to 8k. Right. So this checks out. This is as promised. What is the degree now? So degree of this part, this tensor square and then a square. Let's start with the degree of gk minus 1 by 2. By induction, it is d square then tensor product will make again square, and the path product will make it another square, so that will become d raised to 8. So this much squaring, tensor squaring and then path squaring or matrix squaring, this is giving you degree d raised to 8, so it has blown up. We want to bring it back to d square, so you take the zigzag product. So which implies that the degree of this zigzag with h, right, that will be down to d square. So that also checks out. Finally, the expansion. So lambda gk is at most. Okay, so what is the lambda of this tensor square squared. Tensor square doesn't change lambda, so that is the same as 0.1. But when you do path product, it improves, right? So that is 0.1 square. So that's the first thing. Plus you had a square plus 2b plus b square, right? So now a square is done. 2b is 2 times lambda of h. What is that? Lambda of h was 0.04 plus the square of it. So this you can see is just below 0.1. So that also checks out. Okay, so gk as claimed is d raised to 8k vertex, d square degree, 0.1 expander. Okay, so now we have an infinite family of expanders. Expansion is constant or 0.1 and degree is constant, and the size of the expander is exponential in k. But now we have to check strong explicitness. Is it, how explicit is it? So the algorithm to find neighbors in gk of a vertex v is recursive. That is not surprising because the definition of gk itself was recursive, right? So just follow that recursion algorithmically. So say listing a row in gk minus 1 by 2. Now this row may be very long because gk minus 1 by 2 is an exponential sized graph, but remember that any row has very few ones. Everything else is 0. So non-zero entries are very few, right? Because that is by the degree of gk minus 1, and the degree of gk minus 1 by 2 is just d square, right? So there are only d square, which is constant many non-zero entries. So listing those entries, those positions takes, let's say, t k minus 1 by 2 time, and using this subroutine you can get the expression or even the algorithm, recursive algorithm, to list a row in gk. gk minus 1 by 2, first we see tensored with itself, listing a row there, takes which will again be a sparse row, right? Just it will have how many? It will have at most d raised to 4 non-zero entries. So listing a row there will take twice the time. Because you have, so to check this you have to actually think about how tensor product is defined. Okay, a row will be defined by a pair of indices, one for the first factor and second for the second factor, and so you basically then find row in the first component, row in the second component, and then combine to get the full row. So it will be just you just have to call this subroutine 2 times. So it's 2 times tk minus 1 by 2. So this means that listing all the rows in so now this is for the zigzag product with H. To take the zigzag product, you have to so let me remind you that this row has d raised to 4 sparsity. Only d raised to 4 entries are non-zero. When you are taking zigzag product with H, remember you have to zig inside the first cloud, zag, and then zig inside the second cloud. So you have to actually do this thing twice, right? So you have to compute then all the rows which are required. So there are d raised to 4 rows which will be required in the other square. In the zigzag product. So this will take d raised to 4 times 2 times t k minus 1 by 2 time. Okay, this is what it takes to list a row in GK. So listing a row in GK takes time tk, which we have just shown is big O of d raised to 4 times t k minus 1 by 2. In big O, we are using absolute constant, basically this 2, right? So this is correct in terms of d as a function of d. That much time it takes to list a row in GK. Now in the RHS, you are halving k. So how many times can you halve k? Log k many times, right? So d raised to 4 will be multiplied log k many times. So you will get that tk is equal to d raised to 4 log k times some constant. Okay, that's the time complexity, which is the same as k raised to 4 log d. Okay, so the point is that since d is a constant, this is only polynomial in k, which is polynomial in log of 2 raised to k. Since d is constant. So in terms of number of vertices, this is polylog. Okay. The time complexity is polylog, and you can list a row that you want, and row will have few entries, so you can. So this is how it's proved. Yes, so that finishes the explicit, strongly explicit construction of expanders with constant spectral norm. The last application that we will do, important result that we want to show is given a general graph in the input, can you make it an expander by doing certain operations and without changing the connectivity, somehow remembering the connectivity, right? So, to de-randomize undirected path connectivity, this result that we had, randomized algorithm. So, to de-randomize this, we will need operations to make input graph G an expander without changing connectivity. So, you want an expander, but you also want to remember something about the connectivity of SNT, source and target vertices in G. So, to use this zigzag product, we will need another estimate on lambda G zigzag G prime. The previous estimate will not work because there both A and B were small, but if your G was given in the input, you do not know how small it is. It can only be very close to 1. So, we will use a different estimate, we will prove and use a different estimate next time.